in this section, we're going to be talking about surface integrals. Now, before we jump into surface integrals, we first need to rethink how we describe surfaces in 3 dimensions. All right. So we have previously learned about vector-valued functions. The vector-valued functions of one parameter in 3-dimensional space. When we graph these, we get a curve, right? Well, we could do something similar with surfaces. If instead of depending on one parameter, we write a vector-valued function involving 2 parameters, u and v, then the result will no longer be a curve in 3-dimensional space. It will be a surface. When you think about it, it kind of makes sense. A surface, at its core, is a 2-dimensional object, right? It's flat. It might move in 3 dimensions, but at its root, it's a 2-dimensional object. Just like how a curve, while it may live in 3-dimensional space, it is, at its core, a 1-dimensional object. Okay, so this is going to give me a surface in 3 dimensions, right? There's a real-life example that you're probably familiar with. If we consider the Earth, then we can describe any point on this Earth with only 2 variables. With one line goes this way, let me make it a little bigger. And let's see. No, that's probably our best color. Okay. With one line that goes this way and one line that goes this way. Right? Our latitude and our longitude. And that narrows down a single position on Earth. And so with just those 2 parameters, a latitude and a longitude, you could describe the whole surface of the Earth. Okay? That's what we're doing here. That's the idea. So let's take a look at a few examples. All right? Here we want to find a parametric description for the surface z equals x squared plus y squared. This is just a classic paraboloid. We want a parametric description for the surface. Okay? We want a vector-valued function of 2 parameters that describes the surface. Now, for a surface like this, finding a parametric description of the surface is generally pretty straightforward because we have one of the variables isolated. All right? So if I let x just be my first parameter u, if I let y be my second parameter v, then the equation's telling me that z should be u squared plus v squared. Okay? This describes this surface. It is a parametric description of the surface. All right? Let's take a look at another one that's a little harder. Let's find a parametric description for the surface z squared equals x squared plus y squared. This one's a little different. Now I don't have the z all by itself, right? It's z squared that's by itself. So there are different parameterizations for different surfaces. Sometimes using a different coordinate system may make the parameterization easier, all right? In this case, I can re-express x squared plus y squared as r squared if I switch to cylindrical coordinates. Okay, so if I think about this in cylindrical coordinates, then I could describe this surface using just r and theta. Okay, x is r cosine theta. Y is r sine theta. That's just as usual. Right? That's how we usually define x and y in terms of our polar variables. And then according to this, z squared would be equal to r squared. So I can set z equal to r. And this describes the surface. This is a cone, by the way, a double cone. So if you were to graph this in 3-dimensional space for every r and theta, you get an x, y, z point. If you graph all the points for all values of r and theta, you would get a double-ended cone. All right? Let's take a look at another. Find a parametric description for the surface x squared plus y squared equals 9. This is kind of similar to the last one. This is a cylinder of radius 3. There are no restrictions on z, okay? But since it's a cylinder, maybe cylindrical coordinates are, again, a good idea. So with cylindrical coordinates, we'd have x equals r cosine theta, y equals r sine theta, and then z equals z. All right? Now that leaves us with 3 variables. So somehow we need to use this equation to narrow things down. We know x squared plus y squared is r squared. And if we take the square root of both sides, that means r equals 3. So rather than leaving r as r, for this particular surface, r is always going to be 3. So I can always, no matter what the surface is, narrow it down to just 2 variables. I can figure out where I am on the surface with just 2 variables. Okay? Just theta and z. So my parameterization, my 2 parameters are going to be theta and z in this case. And so I get 3 cosine theta for x, 3 sine theta for y, and my z component is just z equals z. Okay? One more. Find a parametric description for the surface x squared plus y squared plus z squared equals 4. So hopefully we recognize this as a sphere of radius 2. So since the surface is a sphere, maybe we should try describing it using spherical coordinates. So if we recall our spherical coordinates, x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. So again, just looking at what we have right now, we're expressing x, y, and z in terms of 3 variables: rho, phi, and theta. But if this is a parametric surface, we should be able to express this in only 2 variables. And indeed, if you look at this, x squared plus y squared plus z squared equals 4, and convert that to spherical coordinates, we get rho squared equals 4, or just rho equals 2. Okay? So each one of these rows I can swap out for this particular surface with rho equals 2, because we're on a sphere of radius 2. That's what our spherical radius is always going to be. So I can express the surface of this sphere in terms of just our polar angle theta and our azimuthal angle phi. So x is going to be 2 sine phi cosine theta. Y is going to be 2 sine phi sine theta. And z is 2 cosine phi. Okay? So we can pinpoint our position in space with just 2 variables. Those 2 variables tell us what the x, y, and z coordinates in space are, what the x, y, z position are. But we could just use 2 variables to determine the x, the y, and the z, okay, of the surface. But what we want to do in this section is we want to integrate over a surface. So we're going to do this a couple different ways. We're going to integrate a scalar valued function, and then we're going to integrate a vector field. So let's start with the scalar valued function. Okay. Surface integral of a scalar valued function over a surface. So by a scalar valued function, I mean that we have a function where the output, value is a scalar. Okay, it's scalar valued, but it has an output value for every x, y, z coordinate in space. Okay, that's our scalar valued function. And we have some surface. All right, so this is some surface in space. All right, let's call the surface S. All right. Now, what we want to do is we want to integrate this scalar function over the surface. So we want to add up all the little points that this scalar function gives us, all the scalar values over the surface. Okay? So how are we going to do that? Well, right off, we can imagine we slice up this surface. Okay? We could use our parameterization. We're going to parameterize this surface so that any xy point on the surface we can express, we can find using two values, u and v, two parameters. Okay, so we can parameterize it so we would know the x point and the y point and the z point. All right, so imagine we want to estimate what our integral is going to be over just one little square of this surface. All right, so what we're going to do is we're going to take a sample point, doesn't matter which, as long as it's within the square we're looking at. Okay, x star, y star, z star, and then I'm going to multiply by the surface area of that little square. So the little surface area of that little chunk, we'll call it delta S. All right? And we want to do this for every little square along our surface. All right, so it's two dimensions, so we're going to need two summations. All right. This kind of gives us an idea of our notation. The notation we use to represent a surface integral over a scalar function, notation, I can spell, is double integral over our surface, okay, of our function integrated over the surface. Okay, that's the notation we use. All right, let's break this down a little bit using our parameterization. So, our x star, our y star, our z star, we can find that point using our parameterization. There is a particular u and a particular v that would give me that point on our surface, right? So I'm going to plug in u star, v star, and then we need to find the surface area here. So if we think about our derivatives of this vector valued function, of our parameterization here, then the derivative with respect to u is telling me how much I'm changing on the surface as I change my parameter u. Right? So if this line represents a constant value of v, and I'm changing u, then it's going to give me a vector tangent to the surface. Okay? Let me make that a little bigger so we can see it a little clearer. Okay, tangent to the surface. That's going to be the partial derivative of r with respect to u, say. Okay, and similarly, if I take the partial derivative of r with respect to v, I'd be holding u fixed. I'd be holding u fixed, but allowing v to change. So I'd end up getting a vector tangent to the surface in the direction of v. Right? So what we're going to do is we want to estimate the area of this little section by taking the area of something that's a little easier to calculate that's not curved. I'm going to find the little parallelogram, the area of this parallelogram spanned by these two vectors determined by our partial derivatives. Okay? Now, if you remember, that's going to be the norm of the cross product. The norm of the cross product gives me the area of the parallelogram determined by those two vectors. Okay. Now, this isn't quite right. We also have to take into account the size of the region, not just the partial derivative. So we could multiply by some section and some small change in u, some small change in v, and that adjusts for as our change in u and our change in v get smaller, the area will also get smaller, right? We don't want this to always be the same area. We want to kind of shrink it. And as we get smaller and smaller, it'll be a better and better approximation of what we're doing. Okay? And we want to be a little careful here. Okay? Now, since these are just scalar values, I can pull them out of the cross product, and because they'll be positive, they represent distances, I can pull them out of the norm. And this is now looking like a double Riemann sum, a double integral. And so if I take the limit as my number of segments goes to infinity, so limit as m and n both go to infinity, then I end up with a double integral over whatever the bounds of u and v are. Call it d. Okay, of f of r of uv times the norm of the cross product of partial derivatives. Delta u du dv. All right, that's how you calculate a surface integral over a scalar valued function. So the notation we have here, that's how we often express scalar integral over a surface. And then the way we would actually calculate it is we find a parameterization for the surface, plug it into the function, take the norm of the cross products of the partial derivatives, and integrate over the bounds of u and v. Let's take a look at an example. Let's let S be the portion of the cone between z equals 1 and z equals 3. We want to evaluate the integral of the function z squared over that surface. All right? So we know, based on what we just looked at, that if we want to calculate the integral over surface, we need a parameterization. Right? It's a general formula for our scalar surface integral. So let's start by parameterizing our surface. We have z equals square root of x squared plus y squared. So there's a couple ways I could parameterize this surface. I do have a z equals something. Okay, so I could do x equals u, y equals v, and z equals square root of u squared plus v squared. Perfectly reasonable. Okay, or I could notice, hey, I've got a square root of x squared plus y squared here. Maybe using polar variables or cylindrical coordinates, maybe that'd be a good option. All right. So in that case, I could set x equal to r cosine theta, y equal to r sine theta, and z equal to x squared plus y squared is r squared, so the square root of r squared would be r. Okay? Either one's okay. Either one is okay. But notice we want z to be between 1 and 3. So our limits of integration are going to be a little bit different for both of these. For this one, we want our z to be between 1 and 3, so that means root u squared plus v squared should be between 1 and 3, which means u squared plus v squared should be between 1 and 9. Okay? That's the region over which we want to integrate. Whereas this one, my z is just r, so r should be between 1 and 3. Right? Now, either one's okay. Just like when we parameterize curves, when we parameterize surfaces, there's going to be more than one way to parameterize a surface. Either one is fine. Let's take a look at both, and we can see what the difference is once we get to the integration. All right? So let's do this first surface first. Do I want to do that? Maybe we'll actually do this one first. I think this one might be a little bit easier to find the limits of integration for. All right? Oh, and of course, theta. I didn't mention the limits of integration for theta. Theta should be between 0 and 2 pi. Okay, so let's take a look at both examples here. All right? Either way, we're going to need to take the partial derivatives of our vector valued function and then take the norm of the cross product. All right? So let's look at r of r theta equals r cosine theta, comma r sine theta, comma r first. Okay? So let's take our partial derivatives. Partial derivative of the function with respect to the radius. I get cosine theta, sine theta, 1. And partial derivative with respect to variable theta, I'm going to get negative r sine theta, r cosine theta, 0. Okay, so let's take the cross product. Let's drop the norm for now. Let's just worry about the cross product. So ijk, partial derivative of the function with respect to variable r, I get cosine theta, sine theta, 1. And let me just give myself a little bit more room here since components are a little longer. Cosine theta, sine theta 1, and partial derivative of the function with respect to theta is negative r sine theta, r cosine theta, 0. Okay, so the I component, I get 0 minus r cosine theta. The j component, I get 0 minus negative r sine theta, so that's positive r sine theta. But since it's the j component, I get another negative, so it's going to be negative r sine theta. And for k, I get r cosine squared minus negative r sine squared. So r cosine squared theta plus r sine squared theta. And then if I factor out the r, I'm left with cosine squared plus sine squared, which is 1, times the r that I factored out. I just have an r. Okay? Now I want the norm of this. So that's going to be square root of negative r cosine theta squared plus negative r sine theta squared plus r squared. We get square root of r squared cosine squared theta plus r squared sine squared theta plus r squared. Again, I get that cosine squared plus sine squared. Just factor out the r squared first. Cosine squared plus sine squared is 1. So I'll just get r squared here. R squared plus r squared. That's going to be 2r squared or square root of 2r. Okay? All right. I have everything I need to plug into the formula now. Where did I write the formula? Right here. Okay? So I'm going to get the double integral over my region, I'll think about that in a moment, of my function evaluated along my surface. So my function is z squared. I'm going to evaluate it along my surface, which I've parameterized this way. So I'm going to just plug in the r for the z. So I'll get r squared. Times the norm of the cross product, that's square root of 2r. And then I need to think about my limits of integration. In this case, it's pretty straightforward. R is between 1 and 3, theta is between 0 and 2 pi. So if I integrate with respect to r, I should be between 1 and 3, and theta, 0 to 2 pi. Okay? I'll let you evaluate the integral on your own, but that's setting it up. Hopefully the process makes sense. All right? Now, we've done that for one of our parameterizations. Let's take a look at our other parameterization, see what we get for comparison. All right? So our other parameterization is r u of v equals uv root u squared plus v squared. R u v equals square root, equals uv square root u squared plus v squared. Okay, so just as before, if I'm going to plug into the formula, I'm going to need the norm of the cross product of the partial derivatives. Okay, so let's take those partial derivatives. Partial derivative of r with respect to u. I get 1, 0, and this would be 2u over 2 square roots of u squared plus v squared. Okay, which simplifies, of course, if you cancel out those 2's. And partial derivative of r with respect to v. Let's do it over here. I get 0, 1 v over square root of u squared plus v squared. Okay? Now I want the cross product of those. I, j, k, 1, 0, u over root u squared plus v squared. 0, 1, v over root u squared plus v squared. If I take the cross product, first component, the I component, I get 0 minus 1 u over root u squared plus v squared. So that's going to be negative u over root u squared plus v squared. Comma, the j component, v over root u squared plus v squared minus 0. So it's just going to be v over root u squared plus v squared. But since it's the j component, I get negative in front. And then k, 1 minus 0. So just 1. Okay? I want the norm of this. Norm of the cross product. So I get square root of the first component squared plus the second component squared plus the third component squared. So that's going to give me square root of u squared over u squared plus v squared plus v squared over u squared plus v squared plus 1. These have common denominator. If I add them, I get u squared plus v squared over u squared plus v squared. I'll get 1. So I just get square root of 2. Okay? All right. So my double integral here, my surface integral, I want the, becomes the double integral over f of ruv times the norm of the cross product of partial derivatives. Okay, so let's plug in what we know. My function here, leave it over d, my function here is z squared. Go way back to the top. There it is. That's my function. And I want to plug in my parameterization for the surface. So I plug in this for z. So square root of u squared plus v squared squared. Then multiply by the norm of our cross product of partial derivatives. I've already found that. That's right here. That's square root of 2. du dv. Okay? Now let's think about the region over which I'm integrating. I am integrating, where'd we go? Remember, this was our condition. So I'm integrating over the region where u squared plus v squared is between 1 and 9. So let's graph that in the UV plane. Okay. Now in the UV plane, that means that u and v, we're getting circles between a circle of radius 1 and a circle of radius 3. Circle of radius 1, circle of radius 3. And region D is this interior region here. Okay? Now I could try to integrate that in rectangular coordinates and the UV coordinates I already have, but let's make a change of variables and go to polar variables. If I do that, then square root of u squared plus v squared squared, the square root and the square goes away, right? I get u squared plus v squared, but that's going to be r squared. Because I'm making a change of variables to polar, I get an extra r. R is going to go from 1 to 3, right? Edge of this circle, radius 1, edge of this circle, radius 3. And my theta goes around all the way 0 to 2 pi. And I get exactly the same integral that I got before. Okay, that doesn't necessarily always happen. I just happened to make a change of variables that got me to the exact same integral. But the answer will always be the same. Okay, if you tried to integrate it from this form without making the change of variables, which may be possible, you would have gotten the same answer. Okay? I want to take a look at just one more example here. This example is probably simpler than the last one, but there's a little trick here that I want us to be aware of. All right? I want to find the surface area of part of the plane, z equals 3 plus 4x plus 2y, that lies above the rectangle where x goes from 0 to 4 and y goes from 0 to 6. Okay? So how do you calculate surface area with a surface integral? Well, we've calculated areas and volumes before using integrals. So normally a surface integral looks like this. Okay, we're integrating some scalar function f over surface S. In this particular case, since we just are interested in the surface area of S, we can find that if we make our scalar function just equal to 1. We integrate 1 over the surface, that gives us the surface area of S. Okay? Which means that once we find our parameterization, it's just going to be that 1 times the norm of the cross product of partial derivatives of our parameterization for our surface. Okay? So that's going to give us our surface area. All right, so how do we parameterize this function? Well, it's a z equals function. So probably the easiest way in this case is just to make x and y both equal to u and v. And then our z would be 3 plus 4 times the x, which I've just set equal to u, plus 2y, which is v. Okay, so there's our parameterization. And by the way, our u would be between 0 and 4 because u and x are just the same, right? And x stays between 0 and 4. And our y, or our v rather, goes between 0 and 6 because v and y are equal and y goes between 0 and 6. Okay, so that's going to tell me my limits of integration there. All right, I need the norm of the cross product of partial derivatives. So I need partial derivatives. So partial derivative of r with respect to u, get 1, 0, 4. Partial derivative of r with respect to v, I get 0, 1, 2. Let's take the cross product. And I get for I, -4. For j, I get -2. And for k, I get 1. Right? I want the norm of that. So the norm of the cross product of my partial derivatives is going to be square root of the first component squared plus the second component squared plus the third component squared. And I get 16 plus 4 plus 1 squared, 21. Okay, so let's plug that all in. For my surface area, I want the integral of 1 integrated over my surface. So that's going to be the integral of the norm of the cross product of partial derivatives. We just found that cross product of partial derivatives. It's going to be root 21. And the u ranges from 0 to 4, and the v ranges from 0 to 6. I'm over a rectangular region. So u goes from 0 to 4. V goes from 0 to 6. Okay? And when you finish that integral, you will have the surface area of your surface over the desired region. Next, let's talk about vector surface integrals. Surface integrals over a vector field. Okay, now the idea here is that we have some surface. Okay, we have some surface. And it lives inside some vector field, right? What we want to do is we want to find the flux of the vector field through the surface. How much is the vector field flowing through the surface? All right, so maybe our vector field is doing something like this. Okay, so we could definitely see there it's flowing through the surface, right? If we were to imagine the streamlines, you could imagine them going through the surface, right? But we need to know how much it's going through the surface. So the idea here is we want to know how much of the vector field at the point of the surface, so at a point on the surface, how much of that vector field going through that point, how much of it is going to be normal to the surface? Okay, so we can kind of break this into two pieces. This portion of the vector field, it's not flowing through the surface. But this portion of the vector field is flowing through the surface. Okay, so we want to find, so this is the vector field F, and this is, say, a unit normal vector, normal to the surface. We want to know the component of F that is pointing, that orthogonal to the surface or normal to the surface. The amount of the vector field that is normal to the surface is how much of the vector field is actually passing through the surface. We have a portion that's not passing through, that's just kind of skimming along the surface, and then we have a portion that is passing through. So by taking the dot product of F with N, we know how much of this is in this direction. How much of the vector field is in the direction of N. Now, once we do this, this is just a scalar value, a scalar function. And so we just want to integrate this over the whole surface. Okay. This is our vector surface integral. But notice the way we've expressed it, it's a scalar surface integral, right? Because this is a scalar value. So we're going to compute this the same way we do a scalar integral from this point. Okay. Now, I do want to point out that sometimes we use a different notation for this. Sometimes we combine the n and the ds, and we write it as f dot ds with a vector. Okay, means exactly the same thing. Okay, let me actually write that on the other side. Okay, so now that we know that, once we get here, that's a scalar function. So this is a scalar surface integral, just like we had before. So we'll take our function here. We'll plug in our parameterization for the surface. We multiply by the cross product of partial derivatives of our parameterization. Okay. We'll integrate over whatever bounds of u and v cover the surface, the portion of the surface we're interested in. Okay, great. We can go a little further though. All right, because the vector normal to the surface, well, that's just going to be the cross product of partial derivatives, right? The partial derivatives are each tangent to the surface. So when we take the cross product, we get a vector orthogonal to both those partial derivatives. So it will also be orthogonal to the surface, pointing in the direction of the unit normal vector. So this is the direction we want to point. We just need to normalize it to make it a unit vector. So I have f of r of uv, and I'm going to take the dot product and I'm going to replace the unit normal vector with this expression. So partial r over partial u cross partial r over partial v all over the norm of that cross product. And then I still have the norm of the cross product over here too. And you could probably see now that what's going to happen, the norms cancel. And so I get the integral over region D of f of r uv dotted with the cross product of the partial derivatives. Okay, that's how you calculate a vector surface integral. Let me summarize that. So the notation we have is we want to integrate a vector field over the surface, which means we're finding the flux of the vector field through the surface. We want to know how much of that vector field is pointing in the direction of the unit normal to the surface. Okay, and the way we actually find that is we find a parameterization for the surface, plug that into our vector field, and then take the dot product of that with the cross product of the partial derivatives of the parameterized surface. Okay? So this is what we would actually use to evaluate it. These are just nice ways to express the idea. Just one more thing. With the scalar surface integral, it didn't matter how we parameterize the surface. As long as it was a nice smooth parameterization, we get the same answer no matter what. Here, though, there's a couple possibilities. I've drawn my normal vector pointing up. But it's possible, depending on the parameterization, that I could get a normal vector pointing down. The normal vector determines which direction we count the flux as being positive in. So with the normal vector pointing up, we would count flow positive going up, out of the surface. Okay? But if with whatever parameterization I have, the normal vector points in the other direction, then we would, if our flow is going this way, we would count that as negative. Okay, it's going in the opposite direction of the normal vector. So the normal vector determines whether we count the flux as positive or negative. That normal vector could change depending on how we parameterize the surface. Okay, so just be aware of that. That depending on our parameterization, depending on which way the normal vector will face, we may get a positive answer here or we may get a negative answer. Either way, it's measuring the flow in this direction. So if it's positive, the net flow is in that direction through the surface. If the result is negative, then the net flow is opposite of the direction of our normal vector through the surface. Let's take a look at an example. Here we want the integral over surface S of the vector field xy, yz, zx. We're going to integrate it with respect to S. Okay, and S is the paraboloid z equals x squared plus y squared plus 2, where x is between 0 and 1 and y is between x and 1. Okay, and it's oriented up. That's the direction its surface normal should be. All right, so we're going to have to check on that. Now we know that to do this, we're going to need a parameterization for surface S. Okay, so let's find a parameterization for our surface. So there are different possibilities, but probably the most straightforward one. It's a z equals, so I could just set x equal to u, y equals to v, and then z would be u squared plus v squared plus 2. Okay. Since u is x, that means u should be between 0 and 1. And since y is v, y should be between, or v should be between x and 1, or in other words, u and 1. Okay. All right. So I'm going to need the cross product of my partial derivatives. So let's take our partial derivatives. Partial r, partial u, cross, partial r, partial u is 1, 0, 2u. Partial r, partial v is 0, 1, 2v. The cross product of these two is I, j, k, 1, 0, 2u, 0, 1, 2v. And I get, for the I component, I get negative 2u. For the j component, I will get 2v, but it's the j, so another negative. So negative 2v. And for k, 1. All right. And I will not take the norm because this is a vector surface integral. Okay. So if I plug in, this will be over my new region in UV space, determined by these bounds. And I want to plug in my vector valued function. So I'll plug in u for x, v for y, and u squared plus v squared over 2 for z. Okay, so xy is uv, comma v, which is yz. So that will be v times z, which is u squared plus v squared plus 2. And then zx, you know what? I'm not going to have enough room here. Let's take this and move it down so we have some more room. Okay. Temp 2. We have xy, that's uv. Yz is v times u squared plus v squared plus 2. And zx, z is u squared plus v squared plus 2, and x is u. I'm going to take the dot product of that with my cross product of partial derivatives, just plugging into the formula. Right? And just as a reminder of what the formula is, probably write this down. Okay, this is the form we were given. Okay, but another possible form, you could have it as f dot n ds. They're equivalent. Okay, and the way we calculate this is we plug in our parameterization and then take the dot product with the cross product of the partial derivatives. Okay, so this is the formula we're plugging in now. We plugged in our parameterization into our function f. So that's why I plugged u in every time I saw an x, v in every time I saw a y, and u squared plus v squared plus 2 in every time I saw a z. Okay, and then my cross product of partial derivatives, I already calculated that. That's negative 2u minus 2, comma negative 2v comma 1. I'm going to want their dot product, and then I'm going to want to integrate them over space. Okay, so I get first component times first component, negative 2u squared v. Second component times second component, I get negative 2v squared u squared plus v squared plus 2. Third component times third component, I get 1 times u squared plus v squared plus 2 times u. Okay, and I could multiply out, factor out, not factor out, multiply out, expand out, and combine my like terms. Negative 2u squared v minus 2u squared v squared minus 2v to the fourth plus minus 4v squared plus u cubed plus uv squared plus 2u. Okay, and gosh, it doesn't look like I have any like terms. Okay, that's okay. It's still a fairly straightforward expression because I'm just going to be applying power rule, right? Every time I need to integrate. Okay, now let's find our limits of integration. Our limits of integration, u goes from 0 to 1, v goes from u to 1. What that looks like, by the way, in uv space, u goes from 0 to 1, v goes from u to 1. So u goes from 0 to, let's say 1's there. And v goes from u, so v equals u is this line, to 1. So this is the region we're integrating, okay? So I'm going to slice it up this way. So my v goes from v equals u to v equals 1, and then my u will go from 0 to 1. Exactly as it says here. Okay, so I'll integrate. I got all of this to u squared v minus 2u squared v squared minus 2v to the fourth minus 4v squared plus u cubed plus uv squared plus 2u. I'm going to integrate first with respect to v. V goes from v equals u to v equals 1. And then I integrate with respect to u, and u goes from 0 to 1. And I'll leave you to do the integration. But that is how you set up a vector surface integral.